Okay, let's go ahead and get started for getting through what we're going to get through today. This shouldn't take too long. I just want to cover a couple topics here quickly that are related to each other. So we're going to start off with this concept of event-driven programming and then look at what's known as asynchronous I/O. All right, so first off, so far we've been looking at the kind of concurrent systems along with concurrent solutions to problems, and we've looked at ways of handling that, both threads, using the threading module, and processes using the multiprocessing module. And both of those kind of provide a similar way of handling that. You basically create this other thread of execution to handle kind of different tasks that you want to handle in a concurrent fashion, or you isolate them off into their own completely independent processes. So either one of those are kind of similar. The only difference is with threads, they kind of share the same memory space. They're kind of contained inside the same process, so they have lower overhead, but at the same time, they have to share one processor, at least in Python because of the global interpreter lock. And it's rapidly switching the interpreter between those, where processes are kind of contained in their own memory space. And not only are they contained in their own memory space, but they also then have their own Python interpreter running them, so they can be truly parallel. With processes, we also talked about the ability to put them on different machines completely and have them communicate in the form of like a cluster-based architecture, distributed computing architecture. We can't really do that with threads as easily. All right, so we looked at ways of synchronizing, ways threads or processes, ways of communicating between threads or processes, and those are all really kind of useful things to understand and know. And so one of the things we notice is our concurrent solutions, any concurrent program has this kind of non-deterministic execution about it, that it's not fully ordered. If it was fully ordered, it wouldn't be concurrent. So this kind of non-determinism could create problems, and we came up with this synchronization to control that flow. But every program still followed kind of a flow. In other words, it does this, it does this, it does this, and so forth until it completes. So looking at that, a sequential solution, we've seen this before. We start somewhere. A precedes B, precedes C, precedes D, precedes E, and then eventually stops. So the idea here is this is a fully ordered system, but it still follows a flow. And with a concurrent system, we have A precedes, and then in this case, B, concurrent C, concurrent D. These things are allowed to overlap each other, running in separate threads or processes. Eventually, we might join them all together again, and then have whatever happens after they're joined together. So in this case, B, C, D, they could be threads or processes or something like that. But there's concurrent behavior here. But notice there's still a flow through this, even in the concurrent solution. Now, event-driven programming, though, is a kind of a different way of thinking about programs. And it really doesn't work for everything, but for certain kinds of applications, it's a really useful tool to have in the toolbox. But an event-driven program has this kind of event loop. And what the event loop is doing is it's looking for events or messages that come in representing those events. And when an event comes in, the program then does something about that. So the program is basically organized as, when an event happens, take an action that's specific for that event. So note that events usually from some outside source, like you think of a database. It sits there and it waits for a query. The query comes in, it processes that, it returns a response. So you might think about an event-based system as being a web server. The web server waits for a connection. The connection gets open. It receives the request. It fields the request and issues a response in the form of a file being served or some sort of content being produced. It goes back to the client, and then it's done with that particular thing. Now, notice that in those event-based systems, with the events being from some other place, they could come in any order. And so the program doesn't have any way of knowing that. So notice it's not a traditional flow like you think, like an algorithm that goes through flowing from top to bottom, because what it does depends on what events it receives. And that can create a little bit different way of thinking about those solutions. All right. Now, you've probably seen that kind of concept before in programs that you've written, and even written some event-based programs. So, for example, if you've written something in like a Pygame, which is a 2D kind of graphics library and game library for Python, then it very much, when you write a program in that, to get input and react to it, you use some sort of event loop. So events would be like keyboard presses, keyboard releases. It might be the mouse being moved or clicked. It might be the window being resized. But there are events for a whole host of things that we could have the program respond to. So when you press spacebar, we make the character jump. When you press escape, you exit the event loop and terminate the program. And also, if you've written any kind of GUI programs for Windows or really other operating systems as well, there's a window. It receives and processes those incoming events, and it's reacting to those. So you organize your program as, when the user clicks on this object, I take this particular action. Or when the user presses a key and they're on this screen, I receive that and I take this action on it. All right, so to kind of get a picture of what Windows or Pygame or any of those event-driven things look like, you basically have every window. So let's say this is an application window. And this application window, essentially what it's going to do is it just gets events. And the events come in from the operating system. And the operating system window manager decides what event goes to what window. So for example, when you have a window that has focus, it's the one that's going to get certain kinds of events. But there are other kinds of events, like a timer ticking, that might happen whether the window has focus or not. So the idea is that the window manager handles all of that. The operating system itself receives the, let's say, input from hardware. So the keyboard, you press a key. How does it know which window to go to? It goes through the operating system into the window manager. The window manager then decides what application has focus, and it puts that event into the event queue for that application. So now the way we write that application is extract an event from the queue, and then do something with the event, and then just keep repeating that event loop over and over and over again until the queue is empty. And the event queue will have things kind of build up in it, get pulled out of it, build up in it, get pulled out of it. And notice that this is a queue, a lot like we've talked about in previous classes, where the window manager is putting things in, the application window is pulling things out. But we would write our code so that if there's an event, pull it off the queue, process the event, and then continue doing that over and over. And that's one of the reasons why GUI applications can feel very responsive, because they're written in this kind of form like this. Now, the code that handles that would be the event loop for that application or for that window. Okay, so the flow for an event-driven programming would look something like this. So we start up, we do some initialization stuff, and then we enter this loop. Since the star is repeating this multiple times, wait for an event, handle the event, and then repeat. Wait for event, handle the event, until we're done, until we end the program. Now, notice that that kind of wait and handle code is going to repeat indefinitely. What causes it to end? Usually some specific event causes that event handler loop to exit. So an event might be you click on the X on your window in the corner. That sends a special event that says we want to exit the application. We handle that event by closing things down and closing files, or maybe we pop up a box that says, are you sure you haven't saved? But this kind of, we handle that event then causes the loop to exit, and then we finish things up at the end. Now, notice there could be a large number of events that stream into a program. There can be events of different types. And so those events could be kind of ongoing, like timers ticking. It could be keys pressing as somebody's typing. It could be the mouse, even as I move the mouse around on the thing, that's just sending events to the window, lots of them. So all of those things are in that event system. Now, that kind of method of programming kind of gives us a different way to think about solutions. And we think about it in terms of, rather than an algorithmic flow, in terms of what things can happen and how do I respond to each of those, or how do I deal with them. And so that can be ideal for simplifying certain kinds of systems, like operating systems, especially with a GUI. This thing happens, I take this action. They click here, I take this action. They type in this window, I take this action. So also games, this thing happened, take this action. So having a game event loop, the user presses the space bar, make the character jump, and so forth. That could be useful. There are also automotive systems or industrial control systems that this particular event happened. We want to carry out an action that does something with that. So, for example, a new assembly has arrived at this cell of the workstation. What do I do with that? That could be different based on if the cell is available or it's not. It could be different based on the type of part that showed up in the cell. And then take this action. When that completes, that generates an event to cause the next action, which when that completes, it causes an event for the next action. So you notice an industrial control system or a building control system like an elevator, press this button, the system reacts in this way. The door opens. When the timeout is exceeded, the timer ticks. That creates an event. Happens in this way. So event-based programming or event-driven programming can be useful for a lot of different types of problems. And it can, in some ways, be easier to think about those problems than a program flow, per se. So to write code, we need to account for all the possible events that can happen that we need to account for, and then write some sort of event handler for each of those events. Now, that kind of different way of thinking about programming that can create some problems, a lot like concurrency. And also this event-driven programming can offer a way of writing and controlling programs that kind of have concurrent elements of execution. But notice that in this case, it's all done with a single thread. If we go back to that diagram here, notice there's really just one event handling loop that's saying pull an event out, process the event, pull another event, process it. So there's one thread, but we can get elements in here of concurrent behavior. So for example, starting a file download, when the download is complete, it could give us an event that then we do something about that later. So we could have multiple things going on at one time or underway, and events come in that tell us about the state of those later. So back to the idea of a manufacturing pipeline, that something comes into a work cell, that could be an event that we handle. But we could have a lot of work cells running at the same time, each generating those events. Okay, now one of the things that we're going to look at today is that can be a different way of thinking, can also create some difficulties. But one of the things that we're going to do is there's a module in Python that allows us to write code that is kind of fits this kind of event-driven programming way of doing it. And this event-driven programming is kind of considered to be asynchronous because you're starting things. When they complete, they send you an event, or maybe you're creating a process that when you start it, when it's complete, it generates an event that allows the next process to get started and so forth. But it's called asynchronous because we could start more than one thing at one time. When they finish, they could finish at different times. And it's a completely different concept than a synchronous program that has like this flow from top to bottom. The module we're going to look at today is called Asyncio. It's built in to Python. You don't really have to download it or install it. It's a standard module, I guess I should say, rather than built in. But it's very well designed to do the kind of thing that we're after here. Okay, so here's a summary of what that Asyncio module does. That's basically a library to write concurrent code using this async and await syntax. And it provides kind of infrastructure for writing these single-threaded programs that still have concurrent features. And it allows us to use what are called coroutines. But also we can multiplex I/O over network sockets or other resources. We can run network clients and servers. And there are other related primitives to this kind of asynchronous concept. And async I/O is also perfect for I/O bound or high-level structured network code like a web server or something like that, where we want to handle a lot of potential connections simultaneously that all might be in various different states. But when somebody connects, we don't want to wait for them to give us an answer before we move on. So something like a game server might be a good example of where we would want to use something like async IO. Multiple clients connecting for a massively multiplayer game server. We want to handle those when an event happens and they change state. That creates an event. We handle that event and then send something back out to them. Okay, now one of the things I want to look at or highlight here, though, is notice this for writing single-threaded concurrent code using coroutines. That's kind of a key that I want to focus on for a second. Notice that we're talking about one thread, just one thread of execution, but we can still have this concurrent behavior because we can start certain tasks or certain things at the same time with one thread, but they might finish in a different order from one another. So there's still concurrency here, even though we're using just one thread. And the concept here is we're using coroutines instead of thread. And the difference between coroutines and threads, coroutines are kind of cooperatively multitasking rather than what would be called preemptively multitask. And the difference between the two is that a cooperatively multitask system, the threads themselves or the coroutines themselves will give up control of that processor and give it back to be rescheduled for another one. So the idea is a cooperative multitasking system is you're kind of saying, okay, you have time to process now, and when you block for I/O or when you get in a state where you want to pause for a second, I want you to relinquish your control, and then you can resume where you left off on your own without completely exiting the function that's been defined. But you're going to tell me when it's okay for you to say, okay, I need to wait now, so let somebody else have a turn. So it's a way to cooperatively have a form of concurrency. Okay, so this async IO provides kind of both high-level and low-level aspects to the API. Here's some of the high-level one: run and control coroutines concurrently, perform network IO and inter-process communication, control subprocesses, distribute tasks via queues, synchronize concurrent code. So there are some synchronization mechanisms built into this that are at the high level, but we're going to focus on this kind of coroutine thing here for right now. All right, also some of the low-level ones, just quickly. You can create and manage event loops. You can also implement kind of protocols that are efficient, that don't have a lot of time wasted blocking, waiting for things. And then there's this callback-based libraries and code that uses async wait syntax. There's a way to bridge to that. All right, so let's look at the event loop concept. So the core of all systems using async IO is this concept of an event loop. And an event loop is basically, it schedules and runs those asynchronous tasks or those coroutines. It handles asynchronous input and output operations. And it's going to run any of those kind of sub-processes that we create that run inside of there. But remember, this is all kind of a event-driven cooperative multitasking, not like true separate processes. You can combine the two concepts, but this is where we are with this right now. All right, the event loop in this case basically is related to code that uses this kind of async and await syntax. And in order to use that, it has to be on things that are what are called awaitable. In other words, we have to create something that can be used in this asynchronous fashion, and those things are awaitable. Now, the kinds of things that are awaitable that can be used in that await expression are coroutines, tasks, and then what are called futures. And we'll just look at each one of those three things here for a second. So a coroutine is kind of a special kind of function that is awaitable. In other words, a normal function, you call it, and that function then runs through to completion, follows a flow, and then when it's done, it returns an answer to us. Well, a coroutine can be similar to that, except that it's awaitable. In other words, we can not have that block until it's done, but we could start the function and then come back later and get an answer from it and do other things in the meantime. But it's not the same as a separate thread that we're waiting on. It's a kind of a coroutine that can be run with other things that are awaitable, kind of running all at the same time. But when one blocks, it'll allow other ones to be scheduled, and when one finally unblocks and is completed and gives us an answer, we can pull that answer out for that one, while the other ones are still waiting. All right, so how do we define one of these? We use async def in place of the usual def when we define a function. So it's just like defining a function, but we use this async keyword in front of the def. So any function that's defined with async def, that would be a coroutine function. An object returned from a coroutine function would be a coroutine object. So return value from a async def function would be one of these coroutine objects. All right, now moving on to tasks. Tasks are generally used to schedule coroutines to execute concurrently. So in other words, just like you have to call a function, we need to execute, create a task to call a async function. Now, we'll need to make at least one task that will run the event loop. So the event loop is going to be handled kind of on its own. In other words, in Python, using this async IO methodology, we don't really have to have our own like while true do stuff. We can have it handle a lot of that for us. But there usually has to be one task that gets started, at least one task if we're going to use async IO and coroutines that's going to get started. So we can start a task by passing a coroutine to asyncio.run. We'll see that in an example of that here in a second. And to finish this off, futures. Futures are kind of a lower level object. This is awaitable and represents the result of some asynchronous operation that will eventually be produced. In other words, you can think of that like an order that's been placed that will eventually be fulfilled. Think of it like you go to a restaurant. The server comes to your table. They take the order for your food, and you'll eventually get your food in the future, but it might take a little while. But you don't want to be like stopped, blocked, and waiting, like frozen in time waiting for your food to arrive. So you want to do other things, carry on conversation, maybe perform some kind of business planning or something like that while you're waiting for your food. But you know the food is eventually going to arrive. So futures are a way to track kind of those future events that we expect to happen in the future. Now you can have things where something goes wrong and you get a exception that happens. There are ways to handle that with futures as well. So futures are kind of this way of saying, start this operation, and then, hey, you tell me when that's done. I'm going to do other things or take other things. And you can actually start more than one operation. Think about, again, a restaurant. You have multiple people at the table. They all place their order for food. All of those things eventually will get fulfilled. That's multiple different orders that are going to come to the table, but eventually they will in the future. Or if something goes wrong, then there needs to be a way to handle that as well. Okay, so let's look at a simple example here of creating one of these async functions. So in this case, notice all I had to do is import async IO. I also imported time to do, and actually I don't need time here because the sleep is built into that. So I could take that out. But essentially I've created this function. Normally you'd use def, here I use async def, and this is called future print. What it's going to do is says, hey, take this message and print it this number of seconds in the future. So what I do is I would do this await async io.sleep, and what await does is that allows this function, even though it's not complete yet, to relinquish control. So this function now can say, hey, I'm going to relinquish control until this event happens, the event being sleep timing out. And when that does happen, since I'm awaiting for it, then I'll continue on and I'll take care of printing that message. So this is scheduling this message to be printed sometime into the future. And then down here you'll notice I do an async io.run, future print, this is a test 1. And since I did an async io.run here, this is going to wait for that thing to complete, but it's going to be 1 second into the future, we're going to get that thing printed, and then 2 seconds into the future after that, that's going to get printed. But notice this is not running these at the same time the way we have it right now, because async io.run says run this coroutine until it completes. But the coroutine itself isn't actively consuming any processor time here waiting. It basically is just doing this await. So this example here doesn't look particularly different than if we just use time.sleep in a normal function. But it is, because if I were to schedule more than one of these things and run more than one thing at a time, it could be waiting for this one while waiting for the other one, waiting for them to unblock, and those could all be happening in various points of this. And this is why these are concurrent. If we have 2 of these running at the same time, they could both be blocked waiting on some event, the event being the sleep to wake them up, and then they will take some action. So they're all in various states. But notice that when I hit this await is kind of like the thing that yields the processor back so other people can use it. But while I have it, if I have processing in here, It's never going to get taken away from this function until I hit the await. The await is what says it's okay to have somebody else do some work while I'm waiting. Okay, that example was kind of trivial. It's only executing one function call and then the next in the kind of the sequential fashion. So there's not really any concurrency happening there. To run those coroutines concurrently, again, remember it's kind of cooperative concurrency, but to run them concurrently, we need some additional functions to do that. So let's take a look at a few of those. Asyncio.gather takes a sequence of awaitables. So in other words, we pass to this gather function a sequence or a list of awaitables, and it's going to wait for all of them to finish and then return when they're all done. But it's going to run them kind of in this cooperative concurrent fashion. Asyncio.shield could be useful. That's to prevent an awaitable object from being canceled. In other words, you could create some awaitable objects that you say run this until it's done or until I cancel it. But you can make this with shield, you can make it so they can't be canceled. They have to finish before continuing on. Asyncio.wait, that also waits for a sequence of awaitables until some condition is met. This is a little bit different than gather. Gather is kind of getting a list, returning a list of all of the successfully awaited values for each of these. Asyncio.wait is just waiting for them to complete, not gathering the data from them. And then we have wait for, which wait for allows you to wait for a certain amount of time. So you might say, hey, wait for this connection to be created, but only wait for 5 seconds. If 5 seconds expires, wait for will stop waiting for that. So this allows us to create something that waits for a while, but not forever. And then as completed, it's similar to gather, but returns immediately and returns one of those future objects that gets populated later on once the results are ready. And we're not going to spend a lot of time looking at futures today, but note that that's a really useful thing. Again, you want to place your order, you say, rather than saying gather and blocking and waiting for the food to arrive, you could say asyncio is completed, place the orders. That will return these kind of futures objects that then later on will get populated with the results of those things once it's ready to have that. Okay, let's look at a concurrent example now. So this is very similar to that simple example we looked at earlier, but now we have one that's concurrent. Notice we still have the future print function. It still is set up the same way. This code hasn't changed. We still have our await in there. But in this case, what we're doing is we have in our main, what we're doing here is we're saying asyncio.gather. And we're saying I'm going to await this gather to complete. And in here, I have two future prints that are both running at the same time. So these are actually going to get started at the same time. And when I say started at the same time, they're not running at the same time like threads are. It's going to run until one of them has to sleep. And then it's going to run or hits an await. And then it's going to run the other one until it hits an await. And then those are now not going to use any processing power at all at that point until the events happen that wake them up. And then when they wake up, they're each going to print their message. Now, one of the cool things about using asynchronous programming like this is we don't have to worry about, if we did this with threads, they could both try printing at the same time if the times were the same here. We'd have to make a version that acquires a lock and releases it. But here, since it's cooperative, print is totally fine. It can't be interrupted because the only thing that causes us to lose control and give that away to be scheduled to someone else is when we hit an await here to yield processing time back. So in this case, if we think about these running, the first one, this is a test we'll run. It'll say wait for this event, delay event, 1 second to happen, and it'll block. When we hit that await, it now goes to the other function call. So we have one function that's partway through. It's not done yet. And we've already now called another one that's going to wait and do a sleep for 2 seconds. So now we have both of those waiting, one for 1 second, one for 2 seconds. So what's going to happen is the first one, the 1 second event is going to happen first. When that happens, that function now completes, prints out its message. This is a test. And then 1 second after that, at the 2 second mark, goodbye completes, and it prints its thing. So we have two functions kind of running concurrently, each in different parts of that, waking up at different times and then completing their thing. So it's not dependent on the order they're in the list. If I put this as 2 and this as 1, the messages would be flipped. So you can think of this as something that could be useful in something like a, I don't know, like a game that you're writing, where you want different things to happen at different points in time. And you could actually even create these kind of asynchronously defined functions that then trigger other asynchronous defined functions to be fired later. So you could have one event triggering another event, triggering another one. Now, asyncio.run, we still run it. We run main, the single function that then spawns off these two. So we really have three asynchronous functions here all going on at the same time. We have main, which is waiting on these to come in, which is has these two that have been called and created. So we've got all of those. This one won't complete until it gathers all of both of these, and these ones won't complete until their sleep is done and they print out the message. So we have all of this going on at the same time. All right. Now, one thing to keep in mind with await and async is that await can only be used in a function that's defined with async. In other words, await and async are kind of go together. If you want to think about it, the async keyword is telling the Python interpreter, hey, this is a special kind of function that can yield control partway through when an await gets encountered. So think about that async as not really doing anything other than telling the interpreter, we need to treat this function differently than a synchronous function that just runs all the way through. We need to be ready for this to be paused and then resumed once the condition is met that the await is waiting on. Now, note in that previous example, both tasks are scheduled to execute in the event loop. So the execution is overlapped. And actually not just both of those, but also that main, all three of those are kind of overlapping each other, waiting for things to happen. But unlike with threading, that doesn't switch between them on its own without hitting an await. So let me go back to that for 1 second, look at what we're talking about this. In other words, we've got main that's awaiting these to finish. And for those to finish, those two, they get started. They're both waiting on this to finish. And when that finishes, and notice this is a special sleep that's part of asyncio. It's designed to work with asyncio. So asyncio.sleep, when that finishes, one completes, the next one completes. With both of these complete, it allows the main to complete, and then run is now done because all of the things that we were waiting on, or this function we were waiting on, main, is now completed, so that can continue on. So this will still block here. It'll just run these simultaneously, and when those are done, it unblocks this and then continues on. All right, so the gather is simultaneously starting and waiting on multiple tasks. And let's take a look at a use case that's a little more practical here than this kind of future print thing, although that's not impractical. There are cases where you could see where you want some future event, maybe not printing something, but something in the future you want to have happen. Like after a certain number of minutes, then the boss in the game gets unblocked and does something. Okay, so let's think about something we've done in the past with threaded systems, and that's this kind of downloading multiple files. So we're downloading multiple files sequentially. We might have something that looks like this, where we say get file 1, get file 2, get file 3, and so forth for however many we have. And that might be something that would, like a web crawler would do, like Google has to index all of the web pages. So it might be, instead of get file, maybe get web page. But we're going to get all of these web pages, find any links in this, get all of those, find any links in those, get all of those, and spider our way through the internet, kind of gathering the search index of search terms, and then subsequently ranking them later. But that's something that's a practical use case where we want to spider through some entire site and get a whole bunch of things, or get a whole bunch of files off of some server. Now, if we do that sequentially, as we've seen in the past, it's going to look like this. So get file, we have to wait for it to complete. When that one's done, we get the next one, wait for it to complete. And we're going to continue that all the way for the last one. And then finally, once we get the last one, we're done. But notice that means that each of these has to wait. And that also means that even if we have a really short file back here, we got to wait in line behind all these other ones. So this file might be like, I don't know, like 100 bytes, and this one might be 100 meg. We're stuck waiting for this one on that one. And that could be a problem for us. We might want to get what we can as fast as we can to start processing that and not be bottlenecked waiting for something. You know, if we have a really slow server that's giving out this file and really fast ones giving out the rest of them, then this could bottleneck and block for a really long time here. What ideal thing would be to have kind of get all these started, get them all in later, have the shorter ones complete as they can, which could unblock us to do other work on those files and be doing something with those while we're waiting on other ones. Now, here's the sequential version of that program. Relatively simple. Here's just 3 image files from NASA that we're going to download. So I created this download file function and a download all sequential. We pass a list to that. It takes that list, goes through it, basically downloads the file. And here, by calling our download file function that we created down here. And then once all of those are done, then it prints out that they're all done and then stops. Now, down here in download file, notice how simple this is. We just capture the start time, we're using URL-lib to retrieve that document or that file, and saving it in this file, and then computing the stop time. So it's really one line is downloading the file. These 2 are just for the timing. But relatively simple. And then down here we just start download all sequential. So really simple code to get them, but it's sequential. It's going to do this one, and when that one's done, it's going to do that one, and when that's done, it's going to do that one. Doesn't care what size they are, doesn't care how long they take. This one has to start and stop before that one. So this is fully ordered sequential, not concurrent at all. Now, to download multiple files, we looked at using threads for this before, but now we're going to do it in a single threaded variant using async IO. And the way that we're going to do that is we're going to say, we're going to gather and start a process for getting all of these and wait for all of them to complete, and then we're going to be done. So we're going to start them all at the same time, and since gather can now block on each of those and wait for them to complete, we have them kind of going on concurrently or simultaneously. So we're going to use kind of this async io.gather and then wait for all of them to finish. So they're all going to be underway. We're going to still wait for all of them to finish before completing, but that's the way we're going to do this. All right, so let's look at the implementation for that. Implementation is relatively similar to the other one. In other words, I still have a download all, I still have a download file, but I've kind of changed it to _async. We still have our list of things, so this is going to work the same way. One thing that I should have done in here is passed the list in. I think this is a slightly older version I copied this from, but I used the global of that instead. I should have passed the list in to make it similar to the other one, or identical to the other one. But the concept is the same, and it would work if we just passed the list into that. All right, so notice that what we're doing inside here, the first thing is we start this function off with async, and now we have this async with IO HTTP. Notice we're not using URL-lib anymore. We're using async IO and AIO HTTP. And what AIO HTTP is that's this kind of asynchronous IO version of a bunch of functions that are useful for working with hypertext, transfer, web page download, and file downloads. So what I'm doing down here in my code is I'm using the asynchronous version. And all the asynchronous version of that is rather than blocking and waiting for something to finish like a normal function, those are written as async functions that do that. So you could say start this one if it hits a spot where it's stopped, switch to another one. That one will run if it's blocked, waiting on a response, and switch to another one. So it will kind of switch around between those inside of this library by making them asynchronous for us. But in order to use that, we have to say, hey, this thing is asynchronous, using this as that session. And a session is really just, think of that as like a connection to one of these clients. But what we're going to do, I'm still going to go through the file list. And what I'm going to do is I'm going to say tasks.append. I'm going to append one of these async IO ensure future things here for this function, this asynchronous function called download file async. And so what that's going to do, notice this function is laid out the same as the other one previously, but I have passing this session in, which is this asynchronous communication object here to work with. And then I'm going to say await. After this for loop is going to append all of the tasks into that kind of future list that we've had there, tasks. And then after that, I'm going to say await all of those to complete. So in other words, this async io.gather, I'm awaiting on all of those to be gathered from that whole list of all those tasks there. So this is kind of the list of all the tasks. I'll wait for all of those to complete. When they all complete, then I'm done. So that function is the same, except we're using AIO HTTP, and we're putting async in front of that. and we're using gather to make sure they all complete before we continue on. So in other words, gather is going to wait for all of those futures to be filled in, and then we're going to continue. All right, the last little bit of this is the download file async. Notice that that's the same except we pass a session in, and here async with session.getURL as response. I have to change the code a little bit here to read the data. I open a file, I write the data that I receive from that to that file, and I close the file. Since these are image files, I had to do binary on that, but that's pretty much the only difference there is the async here and the async with this session.get, the URL that we got before as response, and then writing it to a file. All right, so when we're done with that, we've now gotten that, and we do that. So all we have to do is do asyncio.run of download all, just like we called the function before. We're doing the same thing. One of the things to notice about this versus threads is that asynchronous functions can actually still return values. So notice I can still return a value from this asyncio.run of that thing. So it's, again, it's not like a thread that's completely separate that runs. These are cooperative multitask functions. So we have functions in multiple states of execution, and they could all return values from them if we wanted to. All right, so a few notes on this, and then we'll be done. That implementation does use that special AIO HTTP module, and that module has asynchronous versions of various HTTP functions. We already mentioned that. But it'll essentially allow us to get data from multiple sources, and if one is blocked and waiting, we can switch to another one. So we're always kind of making forward progress, which can be really useful rather than having a bottleneck. Which means that when I do that file transfer, it's not going to, in the asynchronous version, it's not necessarily going to get them in the order that we specified. File 1, file 2, file 3. It's going to be whichever one finishes first is the one that completes first. Now, one of the things is we need to have, if we're going to use functions with that, they need to be used with async and await. The other thing is that we still need to use asyncio.run and pass the coroutine to that, which has to be an asynchronous function, download all async. And one of the things about that is, like, why did I have to use that special AIO HTTP module instead of just using the typical URL lib? I don't know why that's repeated twice there, but rather than having URL lib .request.url retrieve, as we did before. And the answer is that the URL retrieve is not designed as an asynchronous function. So it'll run and it'll have to complete before we can do anything else. It's not designed to yield. Again, that's not like a thread where it can automatically switch between those for us. It has to be yield. So AIO HTTP is designed to yield when waiting. URL retrieve is designed to complete and block until we have the entire operation. So that's why we had to switch that. Okay, a few more notes here. Other languages support asynchronous behavior like that, notably JavaScript. Running in a browser allows you to do asynchronous function calls. It's kind of standard that everything is asynchronous like that in JavaScript. That can create problems that need to be dealt with. We have to wait for something to complete. And if you've programmed in JavaScript, you're probably familiar with that. And it can be a really powerful tool for handling things like this, especially IO-bound tasks where you're waiting on something a lot. You want to get other things done and be waiting on more than one thing to complete rather than one. Again, think about a restaurant. You don't want to have the server go back and put in an order for one meal, bring that to the table, take the next order, put in the order for that food, wait for it to cook. You want to put them all in at the same time. When they all become available and done, the server gathers them all up on a tray, like asyncio.gather, and then delivers them all at the same time. So that allows these IO-bound events, like waiting for the food to be cooked, to kind of be done concurrently like that. And it makes a lot of sense for the problems like that. Now, other thing is the asynchronous program being a form of cooperative multitasking. The tasks are being executed concurrently, which means that we could have synchronization problems, and we might need to have them communicate with each other. It's cooperative, so it's up to them to hit await to cause it to switch to another one, but they're still concurrent. It's just a cooperative form of concurrency rather than preemptive a preemptive form. But since there's a need for synchronization and coroutine communication, async IO has built into it support for traditional things that we've seen before, like lock, event, condition, semaphore, bounded semaphore queue, priority queue, LIFO queue, are a few of the things that are in there. So we could make semaphores, use them to limit the number of concurrent waits going on at one time or something like that. There are a whole lot of things we could do with this. We could create a lock and lock for a second until this thing completes before allowing other things to complete. Use events to communicate simple things between them from one coroutine to another. And use queues to communicate a lot of different information between a lot of different things. Now, one of the things I'd suggest is investigating that a little bit further. We might look a little more at this at a later class, but we're starting to run out of weeks here, so I want to get through some stuff with deadlock and live lock coming up next. And I also want to get through some things with some other concurrency-related topics, concurrency in other languages and things like that. And also maybe some MPI, inter-process communication, using a standardized library for that. So what we'll do is stop there for today. So that's all for today. Everybody stay safe, and I will see you shortly.